Hello, Assalamu alaikum. My name is Mohammad Furqan and I am a student of Mechatronics Engineering Department at University Islamabad. Here I am going to show you how to make a line following robot using two sensors with their block diagram, truth table and K-maps. I'm going to show a proper simulation of motors running and giving inputs. So first we are going to make how to design a simple line follower using two IR sensors, and using L298 IZ as you can see in our Proteus simulation. So we are going to discuss first that how did we make our logic. So there are there are two simple inputs, S1 and S2. S1 is our sensor 1 and S2 is our sensor 2, and out M1 is our out one motor left one, and out 2 is our motor right one. Enable allows our input. It is like a gate. If enable is on, so our real entries will go through our gates. Like if enable is on, as the input in S1 is in output on M2, the it will be same. Otherwise enable act as a gate. If it is off, then there will be no output on our motors. So there are two bits, S1 and S2, 01 01 01, and here we are showing that if enable is off, then there is no output in our out motors. So we if a line follower is following a black line, so black line and the surface is white, so our sensors will detect white light and it will throw back, because it's an IR infrared sensor. So it will reflect light on a white surface and give signal back. So when our sensors have 00 values, our motor is stopped. If we have a black line straight uh, parallel to the sensor, so our robot will do not move. um, if we have sensor 2 on, then our right motor is on. If we have left sensor is on, our left motor is on. If we have both on, then our both motors are on and it is going on a forward path, straight path. And if our enable is off, then it is going nowhere, it is stationary. So how we going to solve these equation using K-map? We have uh, 2-bit K-map, as we can see here. Let me zoom it for you. There is out 1 and out 2. We will design we will just this is in the SOP form, sum of product. We have written our entities 1 and 1 in M2 and M3. Our common function becomes a, as we said, our simple LFR is using S1 as a direct input. We don't need any gate to change output or input. We just simplified it using K-map. Otherwise we have to use different gate ICs to control it. uh, uh, Similar with the out2, S1 is equal to S out1 and S2 is equal to out2, because our if our left motor is off, that's mean our left sensor is off. So it is a simple basic design. Now we are going to verify it. Here we have designed line follower using L298 motor driver IC. We have connected our output 1 and output 2 DC motors, and we are going to give signal 1 using logic stats. We are going to verify it that if it's going correct or not. um, we are going to simulate. Here we can see that when signal 1 and 1 is on, so out 1 and out 2 are on, out 1 and out 2 are on. and when S1 is 0 and S2 is 1, our O1 is also off. um, if left sensor is off, then left motor is off, and if right sensor is off, our right motor is off. And if they are both high, they are both moving in a straight line. If they are both low, they are stopped, means there is a parallel black line and there is no signal coming and the path is finished. So now we are going to discuss. So to check how much we are spending on a single IC, to know that how much that single LFR in a gate cost. Because of our K-map simplification, we can see that our S1 input is equal to the output O1 and S2 is equal to O2. If here is 0, the motor is off and O1 is also off. So we are using no IC, there are no gates of ICs or any other extra cost. So we are going to calculate that how much did we save, or we didn't spend any extra money on gates, but just by doing simplification on K-map. Uh, uh, how much gates we use? 0 gates we use because of K-map simplification. Per gate cost is 0 into $1 is equal to 0. So I just wrote mistakenly, it's 0 into $1. We are assuming single gate cost is equal to $1. So when we are going to produce 100,000 products, so we are using 100,000 gates. If we use 100,000 gates, it's gonna cost us $100,000. So as we know, we are using no gates in input or output, so just a single IC L298, which is not included in our gate. We just saved $100,000 because of our K-map simplification. So here we calculated the cost and here is our circuit. Thank you. How to make a 3-bit BCD to Escess 4. First we are going to design our truth table. How are we going to access 3-bit BCD to 4? Just add 0 0 0 and a binary number of 4, 0 1 0 to A, B and C. It means that you are going to add 4-bit BCD to binary numbers in 1 to 7, or don't care. Okay, how many inputs do you want? If you have a 4-bit BCD, you are going to add A, B, C and D, and you are then going to add 4 BCD to these numbers. If we add 0, if we add 4 to the 0, it becomes 0 1 0 0, and if we add 0 0 1 and 1 0 0, it becomes 0 1 0 1. In this is called BCD to Escess 4. You are going to add 4 in form of binary number into 0 to 7 binary numbers. Then we are going to write SOP forms of these functions as we have written here. There are so many functions, we are going to simplify it to clear our concepts. So we are designing here K maps. As we know, according to the truth table, we have wrote down our min terms 1 1 1 and 1 at 4 5 6 7 in W function. After simplifying W function, it becomes just an A literal. So rather than designing a function into hardware or Proteus, we are going to simplify it into using K-map. It is going to help a lot or in complex circuits it is going to uh, very easy to solve these functions or display these function in simulation or hardware. So we have solved x function, y function, and z function in a 3-bit BCD, 3-bit K map. How to design a 3-bit K map? Here we have A in horizontal and B in C in vertical. So the first box is 000, second is 0 0 and 0 now 100 1 and 110. We wrote the min terms m4 5 m6 and 7 1 1 and 1 1 here. So after doing combinations we have a common literal is a, so we are going to write down. Likewise we are going to solve these other functions. By solving we have reduced our equations too much. These are simplified form of our equations. So we are going to implement it on Proteus software to check whether these functions are working or not that we have created. So when there is 0 0 0 0 0 0, our w function is off, our x function is on. As we can see we have entry 0 0 0, input 0 0 0, and our x function is on. Y and z are off. Now we are going to check another combination 0 0 1 at 0 0 1 at 0 at 0 0 1, our w function is off, our x function is on, and our y function is off, and our z function is on. So here we can see our truth table is now verified by using Proteus simulation. Our 3-bit BCD to Escess 4 is working correctly. So if you have any other queries and question, you can just ask in the comments. I'm going to reply you, or I'm going to upload video according to that. Thank you.